Today's presentation will be on the topic really at CMP slurry monitoring, particle count and size analysis in CMP slurries. The outline I'm showing here explains it. We'll talk about a definition of large particle counts. We'll talk about how that relates to yield in semiconductor fabs. We'll talk about the mean size of the CMP slurries versus the tails, the large particles. I'll introduce the technology going through the sensors, the laboratory instruments, and the online systems. On the right here, you see the inside of our AccuSizer online mini system. And we'll give example results of, I think, silica, ceria, alumina, CMP slurries, both from the laboratory and also online data. It's been fairly well documented there is a direct correlation between large particle counts in either scratches or defects as you look at what's happening on the surface of wafers being processed using CMP slurries. The graph in the upper left shows on the x-axis the number of particles. Here we're defining large particles as being greater than 5 microns, and the y-axis is wafer count of particles. This is probably taken using some kind of a 10-core surface scan. And we see this direct relationship between the presence of large particles and then the presence of particles on the surface of the wafer. On the upper right-hand side, we see another published study where here we define LPCs as larger than 0.5 microns as measured on the AccuSizer. And these are scratch counts on the y-axis. Again, we see the very linear relationship between the presence of large particles and then scratch counts on the surface. And we just see an image down in the lower right of just one of these scratches showing up on the surface here. So we understand this relationship between the presence of large particles and either scratches or a decrease in the yield rate when processing these wafers. Now, what we can do is look at both the main population of the CMP slurry and then look at the tails. What we're going to look at first is, as you see in the upper diagram here, this is looking at the main population of a ceria CMP slurry. And this was measured using our NICOMP DLS system. And you may be interested in the mean size because the mean size of CMP slurries has a relationship to the removal rate of the slurry. Here we see this has a mean size, probably around 80 nanometers, and you see it being measured using dynamic light scattering. Both the blue line is without filtration and then the pink line after filtration. So we see some change in the width of the distribution after it's been filtered. And what we use using dynamic light scattering, or people also sometimes use laser diffraction to define the main population of CMP slurries, is we see they're down here at about maybe 100 nanometers. But there are also particles present that we call the tails up here greater than maybe 0.5 microns. In these ensemble light scattering techniques, such as dynamic light scattering or laser diffraction, doesn't really have terrific sensitivity to the tails. That's what we use the AccuSizer for. But the NICOMP DLS system can be used to look at this main population. And also the same system can also measure the zeta potential. So you see down here a very steady zeta potential measurement, -8 or so. And this was measured using the same NICOMP DLS system. So we can look at the main population and also the zeta potential using the NICOMP DLS. But to quantify these tails, that's when we're going to use the AccuSizer. So in this slide, now we're looking at the tail. So over here, not visible to this particular sensor of the AccuSizer is the main population. Remember, that was down at 80 nanometers. Here we're measuring at 0.5 microns and above. This is data from the LE400 sensor, which measures from 0.5 to 400 microns. So here we're looking at the tails of the distributions, which were present in that previous graph, but not able to be detected using that technique. And that is what the AccuSizer really is the best instrument available for, is finding these tails and sensitivity to the tails. This is a CMP slurry that was sent to me from the Entegris office in Taiwan. And this is looking at a CMP slurry. The red is no filtration, before filtration. Then it was passed through some experimental filter they were working on. And what you see is there's still some tails here, but see this peak here of these large particle counts? That's what this filter can go in and actually help reduce, minimize, or eliminate. So this is what we're going to use the AccuSizer for, is the sensitivity to these larger particle tails. Here we're looking greater than 0.5 microns, and we'll see various results where we're looking greater than 0.5 or greater than 1 micron, and looking for these tails, which is really what affects the yield or can cause the scratches on the surface of the wafers. We have several configurations for the AccuSizer. It's used both in the laboratory and online. In the laboratory, I show two systems here. On the lower left, the AccuSizer AD, and then here you see the AccuSizer APS. These basically have dilution systems that automatically dilute your sample and then pass them through the sensor, and we have a selection of sensors we'll talk about today, including the LE400, the FX, and the FX Nano. So we match the sensor to the fluidics depending on the concentration of the sample we need to analyze. And then similar options are available with the online system. We call the online systems the Mini, and we can have the LE, FX, or FX Nano sensor built into the Mini system. And we have various dilution fluidics depending on the sample that we're going to analyze and which sensor we load into the Mini. So let's take a closer look at the sensor selection. The first sensor we'll talk about is the LE400. This is a sensor that works from 0.5 to 400 microns. And when we talk about single particle optical sizing, SPOS, this is this technique where we have two detectors. We have an extinction detector and a scattering detector. So particles pass through one at a time through the sensing zone, through the laser beam. We look at the amount of light blocked by the presence of the particles using the extinction detector, and we look at the amount of light scattered by the particles using the scattering detector. We take these two pulses, sum them together, feed them through a pulse height analyzer, which we also call the counter, and then through the use of a calibration curve, we can look at the results you see here, which is a very high resolution technique. So one at a time we look at these particles, and that's sometimes why we need to talk about dilution, because we cannot have two particles present in the laser beam at the same time. That leads to something called a coincidence error. So this is the first sensor, the LE400. The next sensor we'll talk about is the FX sensor. The FX is about a focused laser beam, and we're looking at the extinction signal. Since we focus the laser beam, we reduce the measurement volume. Since we reduce the measurement volume, we can now work at higher concentrations. The concentration limit of the LE400 sensor is on the scale of 10,000 particles per ml. The concentration limit of the FX sensor is on the scale of 10 to the 6 or 1 million particles per ml. So we can work at higher concentrations. Means we don't have to perform as extreme of a dilution. The size range of the FX sensor is about 0.65 to 20 microns. And there is a deconvolution algorithm built into the system to get from the conversion from pulse height to particle size. This is actually the most popular sensor for the AccuSizer Mini systems online is the FX sensor. The next development in our sensors was the FX Nano. And this is where we have a focused laser beam, but we have extinction plus scattering. So an extinction plus a scattering detector, and here we're getting most of the information from the scattering detector. Since we're focusing the laser beam, we can still work at these high concentrations on the order of 10 to the 6 particles per ml. And this sensor gets us down to 0.15 microns or 150 nanometers. So here we have the ability to measure at smaller particles at a very high concentration. The data you see in the lower right is just showing it's still a very high resolution technique, just our ability to resolve 4 different peaks using the FX Nano sensor. So those are the three sensors that we use both in the laboratory systems and online. One of the laboratory systems we could use for CMP Slurries is the AccuSizer AD. Here we take a sample and we pipette it into a dilution vessel. This is not to scale, but we have the dilution of the injected volume to the diluent chamber volume, and then we have exponential dilution. What we mean by that is we're continually adding solvent, which is usually DI water, to the system. And as the sample is brought down through the sensor for measurement, we're continuously keeping this level constant, and we're exponentially diluting the sample until we reach the concentration limit of the sensor. Then we begin the analysis. This is a video of the AD system. So we have various sizes of this dilution chamber depending on the concentration of the sample we're measuring. We simply inject the sample into the diluent chamber, and then we immediately begin this exponential dilution. The sample is now passing down through the sensor, and as soon as we reach the coincidence limit of the sensor, then we begin the sample measurement. So this is the AccuSizer AD laboratory system. The next laboratory system we'll talk about is the AccuSizer APS. Here we have a two-stage dilution system which allows us to work at higher concentrations. And as you look at this diagram, this is the first time we show this concept of a sample loop. So a typical way to use a system is we fill the sample loop, and then this sample loop volume is brought into a dilution chamber. And then there's a second stage of dilution where we continually bring in filtered water. And this way we're continually diluting the system and again bring the concentration down below the coincidence limit before we begin the measurement. There are several ways you can use the AccuSizer APS. We can use a pump to bring sample into that loop, or we can just simply directly inject the sample into that dilution chamber and then begin operating the system. So that's the AccuSizer APS. Let's start looking at some results. This is a silica slurry measured with the FX system, and what we're showing here is this ability of the AccuSizer to detect a small concentration of a spike in the tails of the distribution. So this is the tails of the CMP slurry. Remember, the majority of the population is down here, maybe at around 100 nanometers. And what we do is we spike this with 1 micron polystyrene latex, and we very accurately can see this increase in the concentration of the particles right here at 1 micron. So this is proving the ability to measure this spike down to the scale of about 40 ppm. I then took this same sample and measured on a laser diffraction analyzer. And here is this main peak. It looks like maybe it's 150 nanometers. And I started adding the 1 micron spike, but it took quite a bit before this second peak finally appeared. And knowing the concentrations that we added both to the AccuSizer and to the laser diffraction analyzer, we determined the AccuSizer was 600 times more sensitive than laser diffraction to be able to detect these large particle counts. So maybe if 2 or 5% of the total population is large particles, then the second peak would appear using laser diffraction. But with the AccuSizer, we catch it pretty much immediately. As soon as there's some kind of a spike in large particles, the AccuSizer very quickly notices it and can alert you to that presence. The next examples we're going to look at are for serious slurries, again using the FX sensor. So here we had 2 serious slurries, Slurry A and Slurry B. Slurry B had a few larger particles. The first result you see here is just taking Slurry A and spiking it with a 1 micron PSL spike, and you see it appears right here. Then what we started doing was mixing a small portion of Slurry B into Slurry A. What you see down below is we have the Slurry A plus 1% of Slurry B. And this is looking at the differential distribution where the right y-axis is on a linear scale, but we can see this increase. It might be more visible when we switch the y-axis to a logarithmic scale. And here you see the very good reproducibility first of just the Slurry using the FX sensor, and then this increase in the large particle tail when we add the 1% of Slurry B. The diagram on the lower left, we then inject 10% of Slurry B into 90% of Slurry A, and you see this gigantic increase in the large particle tail. So just proving both the repeatability of the AccuSizer and the sensitivity to be able to find any increase in large particle tails. Here's some data for an Illumina CMP slurry where we use the FX nano sensor. Remember, this is a sensor where we have the best sensitivity down to about 150 nanometers. So here we see it's a fairly clean CMP slurry. This is the differential distribution, and we see the ability to measure down to the smallest possible particles using our systems using the FX nano, and it's possible to use this sensor either in the laboratory or online with the Mini, although it's not the most common sensor to use for the Mini systems for online CMP slurry monitoring. Now, statistics really matter when we're making these measurements. That's a point I want to make with this slide. What you see in this graph is the D10, D50, D90, and if you're not familiar with those terms, if you look at a population, 90% of all the particles are below the D90, 50% are below the D50, making that the median, and 10% of the particles are below the D10. So I'm plotting D10 in blue, D50, and then D90 in green, and what I'm showing is what happens to these numbers as a function of an increase in the number of particles analyzed. So as I measure up to 10,000 particles per ml, what you see is the D10, D50, and D90 are relatively stable. But once I get to this point where I'm measuring greater than around 15,000 particles, then we see this large increase in the D90. And what's happening is if we don't measure enough particles, we really are not fully characterizing the D90. And we need to get to the point of measuring tens of thousands of particles before we start getting an accurate depiction of the D90. What we're trying to do with the AccuSizer is actually find outlying populations. So what we're looking for is actually out here beyond the D90, and we're just trying to detect a few of these outlying tails of particles. So you really need to look at least tens of thousands, hopefully hundreds of thousands of particles before you're going to be able to accurately and repeatably really be able to detect the tails of this distribution. And that's another reason why the AccuSizer remains the most popular instrument for finding these tails, is we inspect enough particles to very accurately always catch these tails, as we see in this result. So here we're looking at a repeat of two slurries where we're looking, again, where we have the y-axis on a log scale, the differential distribution. And you see it's very repeatable, and we're catching these tails both times very accurately. You'll see here the number of particles analyzed in this measurement was 116,000. And those are really the kind of numbers required to be able to accurately find these peaks of tails all the time. And competitive instruments may have some advantages, but if you don't have the statistics, you're just not going to catch these tails, and that's why the AccuSizer is so popular. So we showed some data collected in the laboratory. Now let's start talking about using this instrument online. So what often happens when we start working with samples is we'll measure it in the laboratory, determine the right system, what's the right sensor, the right fluidics, and then we'll start moving to doing the measurements online. And we usually choose something like the LE sensor for fairly clean silica CMP slurries. Serious slurries are typically at higher concentrations. We might switch to the FX sensor for Syria online measurements. And rarely, but occasionally, we'll use the FX Nano if it's colloidal in a very clean CMP slurry and we don't see many particles up at, say, a micron or so. So we can use either of these three sensors. We choose the dilution system, the fluidics, depending on what kind of sensor we have and what kind of slurry. And then the end user determines where to place the online system. And the majority of them typically end up somewhere in the CMP delivery systems, and it's very often downstream of a filter. So we're probably going to stick the Mini somewhere in the CMP delivery system, and now we will have continuous data of large particle count as a function of time. Certainly could be used at point of use, but it's a little more difficult to get it into this kind of position, but certainly that is a possibility as well. To the right, we have the internal fluidics of the Mini system. And you might have trouble seeing it, but here's a sample loop. So I'd mentioned earlier we can inject the sample into a loop before it goes into the dilution chamber, which is shown over here. So if we're going to walk up to a Mini, and with the Mini you can also use it, you could bring a bottle of sample to the Mini, and a pump can bring it up through the system, and we can practice the best way to measure the system, even using the Mini. And one of the things we might do to begin with is say, what size sample loop should we use? Maybe a 1, 0.5, or 0.3 ml sample loop. As we increase the loop volume, we're increasing the number of particles. So if we're dealing with very high concentration CMP slurries, we'll probably use a smaller sample loop. What we want to check for is to make sure we choose a loop where we're not in the coincidence range of the sensor. What you see here are measurements made on a Mini using a 1, 0.5, and 0.3 ml loop. And see how they don't overlay? If we were below the coincidence limit of the system, these would all overlay perfectly. And you see they start overlaying here at about 5 microns. So we probably don't have much of a coincidence issue here, 5 microns and above. But see how with the 1 ml loop, we actually have this turn down in the distribution up here. That's kind of an example of, then we know we're in coincidence error. So we want to make sure that we choose the sample loop in such a way that we avoid coincidence errors. By the way, these tails that you see, this is not a fresh CMP slurry. It's pretty rare you see tails going all the way out to here. But this is just me having fun in the laboratory and showing how you choose the sample loop to choose the best way to measure a system to be down below the coincidence limit. Then we go into the system and start setting it up, and I don't know that I have this perfectly set up for online measurements, but we go into the system setup and we define what's the diluent vessel volume, what are the pump flow factors, what stir speed we want to work at. Then we load in the calibration curve for the sensor. This is the line control menu where we start talking about things such as down here, what was the injection loop size, how long am I going to flush before and after the measurements. Many important settings occur here. And then we can just initiate the measurements, and we'll continuously measure now for as long as we set up the system to operate. So now we've set up our Mini system and we've placed it somewhere inside the processing area. And here is a result where we're just looking at, this is an AccuSizer probably FX result, looking over several weeks, and this is a classic example where, ooh, what happened here? These are just different size ranges. You kind of catch it on most of the size ranges, but it's more pronounced at the larger. Up here, I guess we catch it best around 1.01 micron. So what we're seeing here is a time where we see this large deviation in the large particle count. And this deviation in the large particle count correlated to a major increase in defects for the fab. And this kind of triggered this particular customer to say, oh, you know, usually there are no problems, but when there are problems, that really hits our bottom line. Therefore, this is a pretty wise return of investment, sticking these online monitors into our system to avoid processing wafers when we have these issues. So this led to a large number of installations with this particular customer. Let's look at some other ways you could use the system. Up above, what we see is these are just particle counts at different size ranges as a function of time. And this is looking at what happens as we look at if we're pumping from the top versus the bottom of a tank. And what we see is here at the top, the particle counts are quite lower, but then as we reach the bottom of the tank, we see this increase in large particle counts. And you might consider whether you want to keep pumping out of this tank after you see that increase, or perhaps it's worth moving on to a different tank to avoid this increase in LPCs. Or just here we are pumping from the day tank, and what we just see is, all right, as we change a tote, we see this large increase in LPCs. Maybe we don't want to send this up to the fab, and we want to wait until these particle counts settle down. This is another way the information could be used to make sure that you're sending only the cleanest CMP slurry up to the fabrication area. There are other benefits as well to having any of these instruments either in your laboratory or an online system in your fab. Certainly can use the laboratory systems just to QC incoming slurry. Is the slurry coming in today of the same quality as we've usually been seeing? Maybe CMP slurry has been sitting around and we want to check the stability. Are the particle counts still at the point where they were when it first arrived on the dock? We could use it as a tool to check filter performance, pump performance, maybe use it to choose which is the best filter. This is kind of a study you see in the middle here. This is a slurry where we look at the large particle counts without using a filter, but then once a filter is installed, and look at the decrease in particle counts, and also maybe choose which is the best filter for a given kind of CMP slurry. Up above is actually data looking at what's happening with the pump. This is looking particle counts as a function of time as it's being pumped and saying, is it the best pump? How can we optimize the process there? Down below is again looking at filters, maybe what happens with changing filters, but there's more to deciding how to change your filters than just LPCs. And our experts within Entegris, I'm sure, can help customers have a more thorough understanding of the best way to choose filters and when to replace them. But these are all additional benefits to having the AccuSizer either in your laboratory or in your process to optimize your use of pumps, tubing, filters, and also just to look for these upsets to be aware that this is when you should perhaps alter your production of the wafers. So the AccuSizer, for reasons I've described here, is the best and most popular system for detecting LPCs and CMP slurries. One of the reasons is statistics. We really need to look at least 10 to the fourth particles before you're going to always detect those large particle tails. What typically happens for implementations is start in the laboratory, determine the optimum configurations and conditions, and then install the minis where it's important and where it makes sense in the process, often the CMP delivery system. And I just showed a little data from the PSS Entegris connection, and I think the next time that I address the subject, I'm looking forward to working with our friends at Entegris and generating a lot more interesting data, and also start looking for providing solutions to customers of both filter, material choices, and what impact that has on particle counts.